Okay, so let's get started with our review of the kinetics and potential energy curve worksheet. You're excited, I'm excited, let's do it. So number one says, which mathematical expression represents the heat of reaction for a chemical change? Now we could try and we could memorize things, but I always want you to understand, why is it that the heat of reaction, which we should know, my friends, in chemistry, is delta H, otherwise known as enthalpy, is the potential energy of the products minus the potential energy of the reactants. One way to remember it maybe is through a potential energy curve. If I draw one here, and let's draw an exothermic, which means we're releasing heat, our pathway eventually leads us downward. And we know that the delta H here is the difference of where we start and finish. So this value here is your delta H, and it's negative. Now, how do we get this value? Right? Well, let's pretend that this number here is 10 and this number here is 40. We know it's going down. That's why we say it's a negative number for delta H. How can I get, we know the difference between 40 and 10 is 30, and we're going to give it a negative 30. Delta H here is going to be negative 30. We should be able to figure that out. But when you think about it using an equation, it's 10 units of potential energy for the products, and it's 40 for the reactants. So to get a negative 30, it's got to be 10 minus 40, and that will give us a negative 30. It's got to be the products, or the sum of the potential energy of the products, minus the sum of the potential energies of the reactants. It's the only way we're going to get a value, in this case, a sign that's negative, that's telling us to go down. So the reason why it works is because it's the only way that we can do things so that we get the signs that we need. We know delta H is negative for exothermic, and delta H is positive for endothermic. Of course, that's written for you on the bottom of table I. So again, if I was to draw an endothermic curve, starting low and going high, and let's just make this value here 40, and this value here 10, we can all see the difference where we start and finish is going to be positive 30. So the delta H here is positive 30. It's going up. It's going up. All right, it's going up 30, right? Because this value here is 40, I said, okay? So how do I get that? Well, take the potential energy of the products, 40, and subtract it from the reactants, which are 10, you get the positive 30. So in order to get the values, the sign that we need, products minus reactants works. And notice delta H has to be positive. We're going up in here, going up because we're absorbing energy. Exothermic going down because we're releasing energy. That's the reason why the signs are there. Okay, any case, number one is C. Number two says, based on the heats of reaction of 101.3 kilopascal, blah, 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 chemistry reference table. Hey, that's just table I. That's all table I right there. Sometimes they'll give you that. Sometimes they won't tell you to go to table I. Okay? Okay, so which chemical equation represents a reaction with the heat of reaction? Heat of reaction is delta H, enthalpy, indicates a net release. Net release, my friends, is exothermic. As I say here, it's got to be a negative delta H. Why? Because the energy is dropping. So all I'm asking you to do is go to that table and find the choice that has a delta H that's negative 84. You got to go to the table, find the reaction, look and see on the right-hand side its delta H value, which one is negative. And as I keep saying, guys, if you have a multiple choice scenario, which one's different? They're all positive. They're all endothermic except for choice D. So again, number two is D. Number three, moving on. What is the net amount of heat released? Don't get crazy about this net amount of heat released. All that means is, hey, energy is released overall. It's exothermic. The catch here, though, is they want 2 moles. How much energy is released for 2 moles of C2H6? Now, it said formed from its elements. Kind of another hint there. If you go to table I, they didn't say to go to any table, but you should know this stuff off the top of your head. So if you have a scenario where numbers are appearing out of nowhere like this question, you should know where to look. Hello, This unit is about table I, so you should look at table I, okay? Any case, if we look at the reaction given to us in table I, we see that from its elements, carbon, hydrogen's a Hofbrinkel, there's a 1 in front. For every 1, there's that much heat, notice it's positive, okay, absorbed. So in the way that they gave it to us in table I, because it has a 1 in front, or nothing in front implies a 1, so for every 1 C2H6, there's 84 kilojoules of heat, in this case absorbed. But they want 2. The question wants 2. So if 1 gives 84, 2 is 2 times that. That's all you're doing here. So you take your 84, which is per 1 mole. And again, I know it's per 1 mole because in the reaction they're giving me, okay, it's 1 mole. Okay, so there is 1 mole there. And therefore, for every 1, there's 84. If they want 2 times that. If you want to write a proportion, you can do that. Okay, but it's that simple. Okay, on to C. Based on the same table, table I, which of the following dissolves in water by an exothermic process. So if you go to table I, you're going to see in the bottom third what we call ionization reactions. Okay, and here's an example of one of them. There's sodium hydroxide. They're going to show the water over the arrow, screaming to you that this is dissolving in water. It's not a reactant, so to speak. And this is going to break apart into its ions. And it's going to give you some energy. Okay, so the question is, dissolving in water is not a big deal. It's just about the last third of the reactions on the table that look like that. But if you didn't know, you could have just looked in the table for these chemicals, and you'd find them in the bottom third, written the way that I just showed you, and they give a delta H. Since they said exothermic, I'm looking for a delta H that's negative. And again, if this is a multiple choice scenario, which one is different? Out of the 4 choices, the only one that's negative, which represents exothermic, is choice C. We should know, though, that this dissolving will lead to a higher temperature because exothermic reactions always lead to a greater temperature in its environment because it's releasing that heat into the environment. So this would be like a hot pack, okay? Not that I would pick sodium hydroxide, but hey, I'm tall. All right, so any case, number 5. Here's our potential energy curve. Okay, so what do you want to know here? The first thing that I do when I look at a curve is I see where I start and where I finish. I am finishing higher. The only way that I finish with higher energy, we should know our products are over here and our reactants, is that somehow I must be absorbing energy or putting energy into the chemical bonds, kind of like what photosynthesis does. It puts energy and makes a higher energy compound. Okay, any case, what can be concluded? Well, we're going up in here, because we're absorbing energy. This is endothermic. Our delta H, the difference where we start and finish, is going up. It's going to be positive. And so I have your delta H right here. Okay, and it's endothermic. Okay, now they told us in the problem, though, that every axis represents 100 kilojoules. So every line here is a kilojoule, so I wrote that in. So if we're looking for the difference of where we start and finish, that's what delta H is, and that's what I did here. Hey, that's got to be 200, because every line here is 100. And we do positive because we're going up. Or we're going to do the products. Look at this. The products total energy is 300. The potential energy of the product, I drew this arrow right there. 1, 2, 3. That's 300. Products minus, the reactants. This is the potential energy of the reactants, which is up to 100. So 300 minus 100, 200. So many different ways to do this, but products minus reactants. So in any case, this is endothermic. The curve is working itself upward because it's absorbing energy. And the change has to be positive. Its delta H is positive. Okay, moving on. All right. Number 6, hey, that's going up too. That's also endothermic, but they just want to know what the heat of reaction is. The heat of reaction, a fancy word for delta H or enthalpy, is a difference where you start and finish or going up. It's positive. Don't need that here, but line 2. Let's go with the other lines. This is the potential energy of the products. Number 1. Number 2 is 4, I should say, is the potential energy of the reactants. This one, if you go in the reverse, you got to climb this slide. I call the top of the reaction that activation energy. Okay, or that energy needed to overcome or climb this slide, the activation energy. I should really say that's a kind of an energy barrier, sometimes we call it. But if I go in the reverse, in order for the reaction to go, we got to get to the top of the slide. Now, the energy at the top of the slide, although they don't have an arrow here, is called the activated complex energy. It's the maximum energy we have to overcome when these atoms come together. And when they come together, the energy goes up because they're repelling each other. Atoms or molecules have these electrons, and you need to add energy with sufficient force to overcome that, and that's the activation energy. So this is the activation energy in the reverse. You don't need it for the problem. They're asking for this, but we should know all the other parts to it. So in any case, the answer is B. Number 7. Which one's exothermic? Hey, exothermic, we're releasing energy. Delta H is negative. We should be going down. Really is only one choice, going down, okay? And of course, because it's going down, here's the potential energy of my what? Reactants, potentially my products, and of course the difference where I start and finish is delta H, and this is negative. That's your answer. B is like a heating curve. This could be a solid or a liquid. This could be a solid what? Melting into a liquid. Phase change stays constant. And that's an endothermic, starting low and going high. Delta H is positive. And this could be a relationship that's proportionate. Heck, that could be pressure and temperature, or pressure and volume, but that's got nothing to do with the answers here. So 7 is A, or A. Okay, number 8. A chemical reaction occurs when, well, when you have a change in the chemical formula. The only change in the chemical formula is B. Everybody else, my friends in chemistry, has the same formula, just the phase is different. O2 liquid to O2 solid is still a particle of O bonded to O. So it's a diatomic molecule, but we're not changing that. All we're doing is essentially changing the distance between those molecules, and the same thing with C and D. Remember, we overcome attractive forces or intermolecular attractive forces to change a gas to liquid. In this case, we release heat as a gas becomes a liquid, but again, there's energy changes and phase changes, but these are physical changes. They're phase changes. The chemical formula is not changing. Okay, number 9. Which theory or law is a chemical reaction most likely to occur when two particles with proper energy and orientation interact with each other? Hey, this is collision theory. In order for molecules to react, they have to physically combine. And they have to combine with enough energy to overcome their activation barrier or activation energy. And they have to hit each other in the right spots if they're molecules, not so much atoms. So those are the two things that make what we call an effective collision, which we wrote down here. They love to ask about that, and that's what we're asking about for some of these questions. So, any case, collision theory number 9. None of the other choices are even close. I know we've been doing conservation of matter, but we're not talking about destroying a piece of atom or type of atom or making one or balancing reactions here. So I know that's like, ooh, we've been talking about it, so we should pick that one. No. Okay? Don't fall for that distractor. Number 10, a collision between reactant particles is most effective when particles have proper orientation and proper energy. Remember, the two components of an effective collision that leads to a new bond, a new chemical formula, is high enough kinetic energy and proper orientation. That's what this question is about. So 10 is A. B is the same kind of question, just kind of going from the opposite direction. Hey, a reaction is most likely to occur when the colliding particles have proper orientation and enough energy. That energy, of course, is the activation energy. Okay, number 12. This is going over rates of reaction. And we know that reactions go faster if you increase the number of collisions. So which sample of hydrochloric acid that reacts at the which sample of hydrochloric reacts at the fastest rate with a 1 gram sample of iron? So we're not changing iron, we're kind of keeping iron constant. So we can look right away and say, well, higher temperature, because temperature is proportionate to the average kinetic energy. Kinetic is motion. If you move faster at a higher temperature, and we know that's what happens, you're going to collide more often. So higher temperature is what sticks out first. But there's another factor here, and people forget this. Molarity is a measure of concentration. How much is dissolved? It's moles of dissolved solute over liter of solution. Well, who has the greatest amount of hydrochloric acid? So if I look at the two choices that are at 25, the other two choices are at a lower temperature. So A and C both have 25, but C has a greater concentration of hydrochloric acid, which means there's more of them. So the analogy I give in class, if there's more dancers on the dance floor, what are they going to do? Well, they're going to collide more often. And if they move faster, hey, higher temperature tells you there's a higher kinetic energy to move faster. There's going to be more collisions. More collisions lead to a greater and faster rate of reaction. So that's why that's C. Okay, now let's go on to 13, catalysts. We know they increase the rate of reaction, but they do so differently. What they do is they provide a new pathway. We know that this is the activation barrier right here. This is the activation energy that I always say it's the energy I need to ride a slide. I got to get to the top. So in order for me to react, I need to have a certain amount of activation energy. And this is the activation energy with no catalyst, the red. If I add a catalyst, it adds a new pathway. And that new pathway lowers the activation energy, which means I can climb and ride more slides in the same time period because I don't have to climb as high. The rate of reaction goes faster with a lower activation energy. So you've got to know that it makes a new pathway, okay, and it lowers the activation energy. Okay, that's important. I always say that the catalyzed medicates the hump. Okay, let's move on. That didn't work out. 14. Addition of a catalyst can speed up a reaction, providing an alternative reaction pathway and has a lower activation energy. It's kind of saying the same thing to teach you there. So 13 and 14 are essentially the same. Okay, 15. Given this reaction, which change in the reaction conditions will increase the frequency of effective collisions? By me saying increase the frequency of effective collisions, all I'm saying is they're colliding more often. That's leading to more bonds. It's going faster. So what's going to increase the rate? Okay, well, D is the best answer because it's going to increase the concentration. Why? You're going to add more dancers to the dance floor. As more dancers go to the dance floor, there is more opportunities for more collisions. C is wrong because we're decreasing the temperature. Remember the what? Demo I did with the light sticks. When I put them in ice, they slowed down. They got dimmer. If you put them in the freezer, they stop. A and B are very interesting because you notice that these guys are gases, these reactants. And we should know that gases, their rate of reaction goes up if you push them closer together, if the internal pressure of the system increases. But they said decreasing the pressure. So that would be making them slow down. And you should recognize that increasing the volume is the same thing as decreasing the pressure, right? If you make the space bigger for the same number of molecules, they're going to collide less often. So A and B, although a correct factor for the rate of reaction of gases, is not the right answer here because they're both talking about decreasing the collisions of the gases. If one of these choices said increasing the pressure or decreasing the volume, they would be also correct answers. On to 16. Which compound is formed from its elements? That's a synthesis reaction written in table what? Table I. Table what? Table I. I know this. Okay, so any case, if you don't recognize that now. Now I wrote the reaction as given, and they want to know which one's made from its elements, so it's a synthesis reaction, and is exothermic. We should all know that's a negative delta H, and it's because it's multiple choice. You can look all four of these up and see which one's different, but if you know that exothermic means that you're going down, your delta H is going to be a negative value. And so the only choice there with a negative delta H is choice B. Okay? Number 17. So at these, they're going to say, at 101.3 kilopascals and 298 Kelvin, what's the total amount of heat released when 1 mole of aluminum oxide is formed from its elements? Sounds very similar. Okay? Well, they're talking about table I again. Because if you can create these numbers out of your brain out of thin air, okay, you need a hobby and maybe a life because you're memorizing, these kind of things off the top. You need a table to look at to know these. Okay, so in table I, we have this reaction. And by the way, I wrote it here. This is actually a copy from table I, and there's the reaction. We're making aluminum oxide from its elements. Notice here's the energy, but very careful. Notice that 2 there. That's the energy for 2 of them. They wanted it per 1. So all I'm going to do is I can do a proportion to 2 of these equals that energy. So for 1 of them, it's equal to x. Cross multiply. It's basically, you're cutting it in half. Okay? So we have the energy, but the energy is for 2 of them. They wanted per 1 of them. So you cut it in half to give it per 1 of them, and that's all we were doing for that problem. Okay? It's stoichiometry with energy. This is the energy per mole of this reaction, per 2 moles of this guy in this case. Okay, so in any case, that's choice 1. Number 18. Okay, here we go again. It's going up in here. So delta H is positive. They want to know what the value is because they told you in the problem, okay, each line represents 10. So if I do 10, 20, 30, 40, 50, 60, and what is delta H? The difference of where you start and finish. We're going to go 10, 20, 30, but we're going up. We're going upward. That's why it's positive 30. And of course, it's endothermic because we're ending up higher because we're absorbing energy to do that. So that's why it's positive 30. Okay. Number 19, same idea. We've been through this. Okay. Now, this is a little bit trickier. The activation energy for the reverse. So if we want to go in the reverse, this now becomes the reactants, and this is the products. But in order, we're always starting here. And if I want to ride the slide, I got to get to the top. So I need all of this energy here. Okay, which is the activation energy of the reverse. Now I don't see it here, but I notice I do see C, sorry for the pun, and I do see B. And I can see that C plus B will equal that line right here going all the way up, which is the activation energy. The energy I need to go in reverse to get to the top of the hill. If I want to ride a slide, I got to put energy into it first before I can do whee. Okay, so that's why it's B and C. I needed some value that's this length, and the 2 lines I can add together is B and C. And I kind of redrew them. I drew the B over here and the C here so you can see that. And that's why the answer is B and C, choice D. 20. What is required for a chemical reaction to occur? They got to collide. Effective collisions are the collisions that actually lead to breaking bonds and forming new ones, if it's a chemical reaction. 21, a reaction most likely occur if colliding properties have proper what? Effective collisions, which are orientation and energy. We've kind of hit that concept already. 22. All right, now we're talking about rates of reaction again. Fastest rate of reaction. But now we're introducing surface area. And that was that demonstration I did this week where I took some sawdust, lit it on the table, and it burned kind of slowly. But then I took some of the dust and I blew it over a flame, and it was a faster rate of reaction. So we know increasing the surface area allows more atoms to be exposed so that collisions can occur. So we know increasing the surface area is going to allow a faster rate because more atoms are now able to collide with the reactants. All right, there's more surface for them to do that. And a dust is better than a solid. And we already talked about this factor. You increase the concentration. We call it molarity. It means you're increasing more of them. And if there's more dancers on the dance floor, there's more collisions. So this is a rate of reaction question that has 2 factors, and this is surface area and concentration. C is the best answer. The C is going to lead to more effective collisions over a smaller time because more collisions can occur when there's more atoms exposed and there's more of them to hit each other. That's what this is about. 23. Which of the following statement explains why increasing the temperature increases the rate of a chemical reaction while other conditions remain same? Well, temperature is what? It's proportionate to the average kinetic energy. Kinetic energy is motion energy. If you go faster, you're going to collide more frequently. We go to a bad Grotsky family reunion because we're terrible dancers. When the music goes up, more injuries can occur because we're going to collide more often. Okay? So that's why D is the answer. 24. Okay, as the temperature actually increases, it's expected that the directing particles collide more often. That's what everyone knows, but people forget they're also going to collide with a greater force per collision. That's why some of the collisions at my family reunions can lead to a black eye or a lost tooth. Okay, they're getting hit more often, but once in a while, and they're also getting hit with more force. Okay, as you go faster. All right, and I bring up my family because, yeah, it's a good analogy. So C, which of the following represents the change in potential energy that occurs when a catalyst, I can say it, catalyst is added to a chemical reaction? We know that catalyst does what? It changes the pathway. It doesn't change where we start and finish. It doesn't change delta H. It just changes and medicates the hump. And it lowers the activation energy. It does not change where we start. So C is the best answer. The rest of the choices are changing the energy of the products and the reactants. Delta H does not change with a catalyst. You're just going to change the hump there, going to lower that there, and it winds up lowering the activation energy. Catalysts speed up a reactant by changing and finding an alternative pathway and lowering the activation energy. We're medicating the hump. I shouldn't have went there. Number 26. Okay, a little more challenging question. You should be trying these on your own. If the activation of the forward is 60, that's what this is here. It's the energy I need to climb to the top of the slide. Then the activation energy of the reverse is what we're looking for, this value. Now the key to the entire problem is I gave you the heat. That is the change of heat. That goes right in here. So that's the tricky part, is that that's delta H. And it's an endothermic because the energy's on the what? Reactant side. So if you put a 20 here like I did, so if you know from here to here it's 60, and from here to here it's 20, the difference is 40. Okay, you had to know that energy here is actually delta H. That's delta H, the difference where you start and finish. So if we have this 20, the rest of this is easy. 20 minus 60 is 40. Okay, that's where that came from. The hardest part is understanding that energy in the reaction was delta H there. Okay, number 27 could be challenging. They want the potential energy of the activated complex. Don't get lost in potential energy. They're all potential. The activated complex is the energy to the top of the slide. It's kind of like the height that I would fall when I get to the top. Maybe, I don't know. It's total energy, total distance from the bottom. It's that blue line here. And so what's going to give me that? Okay, and I can see that X, which is the potential energy, it's the activation energy of the forward, right? Energy I need to get to the top of it, plus Y, which is the potential energy of my reactants. If you add these distances together, you will get the activated complex. So you have to know the activated complex is the total energy to the top of the hill. And the two lines that add up to that total blue line are X and W. That's why 27 is A. Okay, which potential energy diagram represents the reaction A plus B goes to C plus energy? Energy is on the product side. You're producing it. You're releasing it. It is exothermic. So I'm looking for a curve to go downward. A and B are going upward. Wrong choices for A and B. They're endothermic. Okay, so these two are not going to work. But between these two, we have to make sure we understand that the reactants are in front of the arrow and they have to be written here. Remember, don't forget, this is the potential energy of the products. Of the reactants. So the reactants in front go on this line, and the product goes on this line. Here we have the products and the reactants. No. When we drew these potential energy diagrams, the products are here, and the reactants are, I'm getting excited. The reactants are always written to start with. The products are always what you end up with. Here they have it flipped. So because A and B are reactants, the reactants start here, we finish here, we finish with C. D is the right answer. All right, sorry for being tall there. And then we're finishing this up pretty classy. We have another endothermic curve. We're going up in here. And we know that endothermic reactions absorb energy. And if you don't understand that, why are we going up? We're going up because energy is being absorbed in this process, and we're putting it into the chemical bonds of the products. Okay. right? And then C and D, if you ever get these choices, they never make sense. Exothermic never absorbs energy, and endothermic never releases. So picking one of those is problematic at best. Okay, number 30, given this potential energy diagram, all right, and we've got A and D, and like before, this is going to be your reactants. This is your products. We're going up in here again, so it's endothermic. According to the heats of reaction, table I, for the millionth time, okay, substance G, people are like, who's G? Well, substance G, as we're making this from A and D, is what? Well, we know it's endothermic. They're giving me these chemicals as a possible G, meaning as a possible product that's being made from its reactants. Because it's endothermic, I'm going up in here. It's got to be positive. So when you look at table I, and I have an example of here, look for these reactions, and here they are in all their glory. There's only one that's endothermic, the only one of the 4 choices. So, of course, it would be C. Okay? And that concludes all the problems. I hope I went over some things that helped you didn't know, or I hope I helped in general. So, good luck with all of this.